Chemist, John Black, Super Chemist. I'm going to go over nitronium ions and how to make them. This is a nitronium ion, NO2 positive. It's an electrophile, meaning it loves electrons, so it must be positive or have some type of partial positivity or lack of electron density in some way. Now, how do you make it? Well, you get sulfuric acid, you get nitric acid, both concentrated. And concentrated nitric acid doesn't mean that it's 100%, it means it's 68%. You do it at 0 degrees, cool them down, to 0 degrees, and you mix them together. That's it. What do you get? Well, an acid and a base, I always say, makes salt water. So what are you going to make? You're going to make salt water. Here's your salt, and here's your water. Now, the first thing you might be saying is nitric acid is not a base. It's even called acid. But in this case, it is a base. Why? Because sulfuric acid is so much more of an acid than this is, that it ends up protonating this acid. And if it accepts protons, that makes it a base in this case, okay, which is rare. Now look here, here's a picture of nitric acid, right? HNO3, 2 and 1 is 3, HNO3. These are your electrons sticking out. Remember, an oxygen has two things, but it also has two pairs of electrons too, and that's what gives it its tetrahedral shape. Here's your acid, your sulfuric acid. I just, instead of H2O4, I put a proton over here because we're going to do a proton transfer, right? It's all about electrons moving. Where do those electrons go? That's what these curly arrows. Curly arrows always tell you where an electron comes from and where it goes. So these electrons are obviously going to pop over here and grab this proton, right? These electrons are not going to go with the proton. They're going to stay with this bisulfate. And what do you get? You get this, right? The proton here jumped off onto these electrons, and here it is, right here. This lost a proton and is now negative, HSO4 anion, right? So this is an oxonium ion. This does not like to be positive. Oxygens are electronegative. They're on the right side of the periodical chart. They do not want to be positive. They want to collect electrons. So what happens is, and you can see also there's an H2O here now. And what's H2O? Water. Water loves to be neutral. So what does it do? It grabs these electrons and it becomes water. Since this had no charge and it just gave away electrons, it's now positive, right? And then this stays where it was, it just moves down. So now you have your nitronium ions. Now, one of the most important things about this reaction is to do it at 0 degrees Celsius, okay? You don't do it at 50 degrees, you don't do it at 60, 70, 80, you don't do it at 30. You do it at 0 degrees Celsius, okay? So you mix these two together, so what? So now we mix them together and we have a bottle of water and this salt, where the cation is NO2, or nitronium ion. So what? We have a glass full of nitronium ions. What are they good for? Well, I'm sure they're good for a lot more than what I'm telling you, but I'm going to give you two examples. Nitration reactions, right? Like when you make nitrobenzene from benzene, right? You have benzene and you want to put a nitro group on it. What is a nitro group? It's NO2. Boop. This is positive, and what's benzene? It's not negative, but it sure has a lot of electrons since it's all in a big circle there. It's all, you got electron density, it's like, a lot of electron density. Not negative, but a lot of electron density. And what does this look for? It looks for anything. It likes electrons. It doesn't care if it's negative. If there's electrons and there's an excess of them in a group, then it wants to get over there and do something with them. What's another thing you can do? You can make nitrate esters. What's a nitrate ester? Here's a couple examples. Nitroglycerin, nitrocellulose. And I know they say nitro. Those are not nitro groups. They're nitrate esters. It's just back in the day they didn't know, so they called them nitro. And you know how that is with old names. They don't like to give up the old names even if they're wrong. So there's a couple examples. You might say, well, what's the difference between a nitro group and a nitrate ester? Now I'm talking about esters. An ester is a combination of an acid and alcohol. Usually to get them together, you add some heat and some sulfuric acid to catalyze it. But what is, if nitrocellulose is an ester, right, where's the alcohol come from? Obviously nitric acid is the acid, right? Sulfuric acid, we mentioned, that's the catalyst. We've never mentioned, and we say that the cellulose is the alcohol, but why is that? Cellulose is just cotton. Okay, that's why they call it nitrocellulose gun cotton. But what is cellulose, or what is cotton? Cotton is just sugar. Okay, cellulose is chains of D-glucose sugar, or dextrose sugar. Okay, and what is glucose, or dextrose, or D-glucose, dextrose, whatever? It's just a monosaccharide. It's just a sugar monomer. Monomer, saccharide, sugar. It's a single sugar unit. And what is sugar? Well, there's two examples of sugars. There's polyhydroxyaldehydes and polyhydroxyketones. And what does that mean? That means there's a whole bunch of alcohols, hydroxyl groups, hydroxy group. There's a whole bunch of them on an aldehyde, or there's a whole bunch of them on a ketone. Right? I mean, this thing has a bunch of alcohols, polyalcohols, polyhydroxys, right? So that's why cellulose, you can, and the same with glycerin. Glycerin is, it has 3 carbons and 3 alcohols on it, on each carbon, right? That's why you can make nitroglycerin. Nitroglycerin is the nitrate ester of glycerol. The nitrate ester of cotton or cellulose is cellulose, which is a polyhydroxy, either aldehyde or ketone. That's where the alcohol comes from. Now here's a mechanism for making an organic ester, meaning from an organic acid like acetic acid or formic acid, you know what I mean? This would be your pathway. Now I did the same exact thing for nitric acid, making an ester. X would be, this is the alcohol here, but I used X because it's a sugar and I don't want to draw a big complicated molecule, so I just put X there. But I do not think this is the mechanism, because I don't see any nitronium ion, and I don't know. I don't think that's it. I think what happens is it's more like this down here. We have your nitronium ion. It basically comes in and replaces the hydrogen or the proton on there. You know what I mean? These electrons come in, grab the positive nitronium ion, then they kick the hydrogen off so that it can become neutral, and you end up with this. But like I said, I'm unsure of the mechanism for this, but I do believe it's something like this. This would be the analog to this, but I don't think that's the way it goes. You can see how look over here, this is an organic ester that you're familiar with maybe. And look at this, you've got the same thing. You've got an alcohol, right? Just like up here, you got an alcohol that lost its proton, right? This is just a sugar part, but as you know, sugar is just an alcohol. And then you got your carbonyl. In this case, it's with a nitrogen instead of a carbon, but you can see it's a double bonded to an O, double bonded to an O. Then this is just the rest of your acid. In this case, it's always going to be an O because it's nitric acid. There's only one nitric acid. There's a million carboxylic acids. You know what I mean? You can have this chain being whatever. You know, it could be 3 carbons, 2 carbons, 100 carbons, whatever. But the point is, look how similar they are, right? And look how the nitrogen, the NO2, what's it connected to? It's connected to an oxygen. And you know why? Because that's the part of the alcohol. Here's the alcohol, and here's the acid. And all together, put together, it's called an ester. And that's what this is, an ester. nitrate ester. Now, what's a nitro group? Now, this is a nitro group, nitrobenzene. Look at how the NO2, what's it connected to? Is it connected to a oxygen like an alcohol has? No, it's connected to a carbon. That's how you know that's a nitro group. Now, I want you to notice something, and either way it goes, you always end up with protons at the end. That's why this sulfuric acid is technically a catalyst, okay, especially in this one right here. And even down here, you'll notice you do it this way. You always have a proton coming off to replace that proton that was used to make this nitronium ion. So the sulfuric acid technically is a catalyst, no matter how you think of it, whether you're talking about organic esters or you're talking about inorganic esters like a nitrate ester. The sulfuric acid is basically just a catalyst. That doesn't mean you use it small amounts. That just means that the proton is replenished and the sulfuric acid is replenished. That's all it means. So I want you to look at this. This is a little section of cellulose, which is just basically sugar. Here's two monomers. You know, here's a glucose, they're connected together, and then the chain goes on. That's what these parentheses means. It goes on and on. I want you to see there's 3 hydroxyl groups on each thingy. That's why you need to nitrate 3 of them. That's why you need 3 nitronium ions for each glucose monomer that you have here. So what does nitrocellulose look like? Look at how the H's are green. Now look at them. As you can see, all I did was put an NO2 where I took the H off and I put an NO2 on. There's your nitronium ion. That's nitrocellulose. Okay. This is why I'm going over this more, because this is the first thing I'm going to use my nitronium ion for, is to make some nitrocellulose. And I'm just going over a couple, well, the way I'm going to go over it. This is, you know, I see a lot of people on the thing, you can make it from potassium nitrate and sulfuric acid. But this is how they do it in the, like in a lab, okay? Yeah, what I'm going to do, right? So here's your formula, right? You need 3 times as many nitronium ions than you need cotton or cellulose. And you need some sulfuric acid in there as a catalyst, 0 degrees. You get 3 molecules of water, and you'll get your nitrocellulose, each monomer. Okay? You want to keep everything as cold, close to 0 degrees Celsius, but not freezing into a solid. Okay? What good is a solid? How's anything going to interact in a solid? 2, I'm going to pour my nitronium ions onto cotton, and then stir it and smash the cotton into the acid and make sure it all gets in contact with it, right? Store it for 24 to 48 hours, keeping it at 0 degrees. Then wash it, and then repeat this whole process again. Nitrate it a second time. That's how you're supposed. Am I going to do it? No, I'm not going to do it twice. It's crazy. But that's the way you're supposed to do it. You do it a second time to get all the parts that didn't get nitrated the first time. Okay? Then you wash it. Okay? And when I make the nitrocellulose, I'll go into details about how I wash it. And that's a very important thing, washing. If you don't wash it right, it could spontaneously combust at any time, any second. This is a very dangerous thing to make. You know, I want to be making no large amounts, that's for sure. But that's basically it. That's the whole instruction. Now, this is not how you make nitroglycerine. Okay, you can't just transfer these over. I know I say if you know how to make one thing, you know how to make them all. In this case, because it's explosive, I would not transfer things over. For one thing, nitroglycerin, you use fuming white nitric acid. You know what I mean? Here you're using concentrated nitric acid, which is 68 to 70%. Okay? Fuming is like pretty much 100% nitric acid. Alright? There are differences on what you do, so don't just transfer this over to something else. Okay? If you do this, you do it at your own risk.